Hello and welcome to another video. In this video we're going to be working on case symbol and grammar. And so here you're building a table of n rows, one index, and you write 0 in the first row, so we can write 0. And every subsequent row we replace every 0 with a 0, 1, and every 1 with a 1, 0. So if we draw out a few rows, we will have 0, then we will replace that 0 with a 0, 1. Then for the next row we replace this 0 with a 0, 1, so we have 0, 1, and then this 1 gets replaced by a 1, 0, and then one more row. So this 0 replaced by 0, 1. Then we have 1, 0, and 1, 0, and then 0, 1. And that's like 4 rows. So for our outputs, and these are all one index. It's like row 1, row 2, row 3, row 4, column 1, column 2, column 3, and so on. So for row 1, column 1, it's going to be this element here. For row 2, column 1, it's this element here. And for row 2, column 2, it's this element here. So how do we actually get this like super deep, right? Because this could be like 30 rows down. And the problem is you can't really write these out. There might be a way to do it because you do notice that kind of like you're keeping your old stuff and you're just adding on to the end. So there might be something there. I'm not entirely sure. And there might be a way to do it. But the more intuitive way is the reason you can't write these out is because this is like 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3 elements, right? So the problem is, I think the constraints here is like 30 rows, so you get like 2 to the 30th, which is like a really, really big number. So you can't just like manually build the tree. So if we can't manually build the tree, what else can we do? Well, what we can actually do is every node, like every 0, has children 0, 1, and every 1 has children 1, 0. So we can actually write this out as a tree like so. So we'll have the first row like this. Then let's make sure we have enough room here. So the second row will look like this, 0, 1. We're just going to write out 4 rows again. The third row will look like this. 1, 0. And finally, the last row will look like this. 0, 1. 1, 0. And you can keep doing this, right? So you can keep doing this, but we're just going to write out 4 rows because this is going to be enough for our example. 0, 1. So essentially, you can keep doing this. You can keep, like, for the next row, the 0 would have 0, 1, 1 would have 1, 0, and so on. And so the number of nodes at each level multiplies. And instead of actually doing this one index, we're going to convert it to 0 index because the math is going to be a little bit better that way. So what we actually are going to want to do is we're going to use some tricks for complete binary trees to figure out the index of our parent, essentially, like kind of where it is, and where, like what should be the column value of our parent be, pretty much, and then, you know, like where is it relative to our node. And so let's show how we're gonna do this, and we're gonna do this 0 index to make it easier. So obviously we're not gonna draw out the rows here, so the rows are kind of straightforward, right? This is row 0, row 1, row 2, row 3. We're just going to draw out the columns. So instead of having the columns 1 index, we'll have them 0 index. This is column 0, 0, 1, 0, 1, 2, 3. Right? And this is basically saying, like, for the row, if you were to just write out these values in a line, what location would they be? So that's pretty much all you're representing. 3, 4, 5, 6, 7. And let's say we were asked to get, for example, something at n equals 4. Right, this fourth row, this is 1 indexed in the actual problem, but we're gonna convert it. And k, let's say, is 5, right? So this value here. So we don't know this value, right? Like all these are basically question marks, so we don't know any of these. So essentially, let's just write it out as if we don't know it, right? So let's not actually have these values. The only value we know is this one up here. So we know like this is the tree structure, but we don't actually know these values because we're not going to pre-compute the entire tree, right? It's too big. So the only thing we know is like we are here. So what we're actually going to do is first we're going to convert this to 0 indexed. So 0 indexed 4 would be 3, and 5 would be 4. Right? So this is what we're going to have. So actually, technically, the value we would really be asking for is this value. And that makes sense, right? Because for k equals 5, if this was 1 indexed, k equals 5 would be here. It's the 5th value. So this is the value we are looking for. Okay. Now we're going to use the tricks of completed trees. So we know that like every level is fully completed, right? So every level is fully completed. So if we know the index of a child, we can figure out the index of a parent. So here the index of a child is 4, but how do we know the index of a parent? Like this is the column index. The row index is obviously going to be like 3, 2, 1, 0, right? But how do we get this column index? And so the way to do this is for a completed tree that every level of the nodes are 0 index like this, right? Like 0, 1, 2, 3, 0, 1, 0. And if you've implemented like a heap before or any kind of completed tree, figure out like where the parent index is and the child index in an array, then this is going to be kind of familiar to you. But essentially, for a node, its children, like if a node is at index n, its children are going to be at index n times 2 and index n times 2 plus 1. And let's kind of see how that makes sense, right? So for like this node, and this is the column. This is the column of the, so if it's the parent, then the child is over here. So let's kind of show how that's going to work. So if this is column 0, then n times 2 is 0, and then n times 2 plus 1 is 1, right? So 0, 1. Then if you take some random column like this, 2 times 2 is 4, and then the other node is going to be at 5. So that's how you get the children from the parent. Now, the way to get the parent from the children is also pretty similar. So you don't need to subtract 1, but what you do need to do is you just take the children column and you just floor divide by 2. And for example, if we have 5 and we floor divide by 2, we would get 2, which is correct. 4, 2, 7, we would get 3, 6, we get 3, and so on. So now we are able to get the parent's column from the child, but we need one more thing, right? We need to know, like once we can get the column, like let's say we are at 4, we can get 2, but we also need to know, are we the left or the right child of the parent? Because then when we get the parent value, like let's say this is 0, if we're the left child, 0 goes to 0, 1, so we know this has to be a 0, but if we're the right child, it has to be a 1. So we have to know the parent index, and we have to know if we're the left or the right child. Now looking at this tree, can you figure out, and you can pause the video if you want, how to figure out if you're the left or the right child of the node above? And so hopefully you thought about that, and basically the way to do it is, as you notice, this is always going to be a complete tree. So in a complete tree, your children are always left, right, left, right, left, right, left, right. Right? So every even index is left, and every odd index is right. So we can just simply take the column, and if it's even, then it has to be left, and if it's odd, it has to be right. So now that we have both of those, we can actually kind of simulate what our function is going to look like. Essentially, what we're going to do is we're going to get the parent index. Let's say we are looking for this value here, right? We can get rid of this. And we're starting here, and we're going to say, okay, what's our parent index? Well, it's up here, right? 4 divided by 2 is 2. And what's the, and are we the left or the right child? Well, we're even, so we're left. So we're going to write a little left here to represent that. So we're going to recurse up here, right? And we're going to say, okay, well, are we, and our base case, remember, is over here. So the way we're going to recurse is pretty straightforward. We're just going to take in row minus 1, right? Because these rows are 0, 1, 2, 3. So to recurse up a row, you do row minus 1, and then for your column, you just do the column of the parent. So for this one, what's the parent? It's going to be 2 divided by 1, which is 1. And is it left or right? Well, it's even, so it's left. So we're going to draw a little left. Now we're going to recurse up here, and we're going to say, okay, we're still not at row 0, we're at row 1. So what's its parent? Well, its parent is 1 divided by 2, which is 0. Now, is it a left or the right child? Well, it's odd, so it's the right child. Then this is our base case that we recurse up to. So if this is our base case, we will just return 0. So now we will return 0 over here. And if this is 0 and we are the right child of 0, remember 0 goes to 0, 1, and we're the right child, so this has to be 1. Then we will return over here. We're going to return 1, and we're going to say, okay, well, we're the left child of 1. 1 returns 1, 0, and we're the left child, so we have to be 1. Now we're going to turn 1 down here, and we're going to say, okay, well, we returned 1, we're the left child, so 1 returns 1, 0, so we have to be 1, right? Because this is 1, 0, this is 1, 0, and this is 0, 1. And then that would be our answer. So essentially, to recap, 1, get parent, call floor divide 2, figure out left or right, left is even, recurse up, row minus 1, call mon2, base case, get up there, and then return to the child and have a bunch of if statements, right? Depending on value and left or right, get child value. And that's pretty much it. So we can code that up now. So what we're going to do is we're going to have a helper function here. So we'll say def traverse row column. We're going to say if row equals 0, that's our base case, right? That's the number we have. Let's return 0. Now we're going to calculate a parent, and we're going to get a parent value. So we can just say parent value equals traverse row minus 1, and then the column. The column should be call 4 divided by 2. And from here, we just have a bunch of else ifs depending on the value and our location. So if parent val equals 0, if column12 equals 0, then we are the left child. So 0 returns 0, 1. And if we're on the left, we have 0. So let's return 0. And if we are the right child, let's return 1. And otherwise, if the parent value is 1, if we are the left child, then let's return, so if we're returning 1, if we're the left child, we're going to be at 1, right? Because 1 returns 1, 0. So for the left child, we will return 1. And if we are the right child, we will return 0. And let's fix that. And finally, we just need to call our function with traverse. And remember this problem originally, everything is 1 index, but we made it 0 index for all the math to work out. So we need to make it 0 index by just subtracting 1 from everything. So like n equals 1 and k equals 1 would be equivalent to n equals 0 and k equals 0 for us. And let's give that a go. And looks like it works. And there we go. So pretty efficient algorithm. And let's talk about the time and space here, not JavaScript. So essentially what we are doing is we are recursing from the leaf of a tree up to the root. So we're essentially recursing up the height of a tree. Now it's always going to be a fully completed tree. It's never imbalanced or anything. And the height of the tree is just going to be the number of rows, which is n. So we're just recursing all the way up. And for our space, we don't have any extra data structures, but our recursive stack frames is also going to be O of n because we're recursing up the height of the tree. So we have to hold those frames in our memory. And yeah, that's going to be all for this one. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. I will see you in the next one. Thanks for watching.